All right, so we're gonna do ideal gas law. We kind of worked on that a little bit last year, and so I'm just gonna write that down. Let me move this out of the way. Okay, so this is ideal gas law, and I'll explain what each letter means in a second. So it's basically pressure, volume, and temperature, the relationship, but it's weird because the ideal gas law, there's like 4 different variations, and so sometimes we consider like the number of particles, and then sometimes we don't. Like if it's a contained system, but then sometimes we have to figure all that stuff out. So a very common expression is this one here, and it's the ideal gas law that uses the number of moles, where the number of moles can be lowercase n. All right, rather than using the number of atoms in a molecule, and that's the capital N. So that's the number. And I like to say particles. Molecules, sometimes people get fixated on atoms versus molecules. And so I'm going to say the number of particles. Right? And that kind of makes a little more sense. It depends on the textbook you read. Sometimes they'll say particles, sometimes they'll say molecules. But I never want, because like if you have a molecule of water that's 3 atoms, so what is it? So we're just talking about particles. And so then if we take this and then we multiply by Avogadro's number, and so that's a funny thing. If we say Na, and that's Avogadro's number, and we'll do a separate slide on that. Right now, I don't want to put all the numbers in. I just want to focus on that stuff. And so we're going to derive a formula. Hi. Thanks. There you go. So then, to derive this, let's recall a couple of things. That the number of moles is equal to the number of particles divided by Avogadro's number, like this, Na, right? And so in order to get this kind of thing going, and remember also I forgot to define K. K is Boltzmann's constant, right? I forgot the Z. So then we can in a fancy way plug this back in. So the way that would look is if we say P, PV, and P is for pressure, V is for volume, T is for temperature. And so we'd get capital N over NA, and then right, NA times K. That's the same thing, right? Because the NA and the NA cancel, right? if I multiply by Na here and I divide by Na, they kind of cancel. And so when you do that, we can define the universal gas constant as R. So we'll call this the universal gas constant R. And that's just going to be N A times Boltzmann constant. Okay? And the reason that we're doing all this stuff like this is because sometimes we have information and knowing the different formulas. Sometimes, for example, you're always going to have Na, which is Avogadro's number when we're talking about particles and moles. So that's always going to be there. It's a constant, right? And then you're always going to have Boltzmann's constant. So rather than write out that number, those two numbers every time and do the calculations, just put them together. Does that make sense? But we always want you to know where things are because, I don't know, maybe 5 years from now you're a chemical engineer or something, and so you'll need to use that information. So then you can just rewrite this, right? You could say PV is equal, and if I take this and substitute in the n, lowercase n, and I take this and I replace that with the universal gas constant, you get this, okay? And so all of that is or a couple of different representations of the ideal gas law. Does that make sense? I'll give you guys a second to write that down. And we'll deal with the numbers later. I'm going to move to the next slide in a second, and then I'll...
I think your first notes went over that stuff a little bit, or like the AP assignment, one of the two.
Okay. Well, we're going to do some actual problems in a second with that. I'm purposefully explaining stuff just in case. Yeah. Yes?
Under the universal, like R equals like NAK, is that A like supposed to be capital next to the N? Or?
I think they're all supposed to be capital. Okay. So this one, okay. Yeah, I'm sorry, this should be capital here too. And yeah, they should all be capital. My bad.
Okay.
Oops. Oh, and I'll put one last thing. So this value here for R, Avogadro's number, if you remember correctly, is like about 6.02 times 10 to the 23rd times 1.38 times 10 to the negative 23rd. And I don't know if I have room. We're going to squeeze it in here. You guys might have to stand up to see it, but it's 8.31. And there's units. I didn't write all the units in there, but it's going to be joules per moles per K. Kelvin. That's the temperature per Kelvin. And the units are important because when you plug it into the formula, all the units will cancel out, and that's how you get the pressure times the volume and all that stuff. So this is not a one. I was going to put this in a box. I got sidetracked. So rather than write this out and write this out every time you do it, the second formula is a lot easier because R will be the same every time. Okay. And so because atoms and molecules can be calculated in molar mass, then you can weigh things. So this is more practical. Or you can, I shouldn't say weigh. find the mass of certain objects. Okay. And then we could rewrite this in other units. Give me a second here. Let me see what the next slide is. Yeah. These are in the textbook. I'm starting to. Do you guys have all of this written down? Okay, let me do this real quick because I'm running out of space here. So then R can also be written in other units. So, because we're measuring a lot of things, we're measuring energy, right? Joules is energy. So if you convert that number of joules, the energy part, to calories, lowercase c calories, then you get this number. Whoops, not divided by, times. Oh, I don't want to erase all of it. That's the only bad part about this. So R is equal to 1.99 calories per and then if you convert that, this is well, I'm sure we're going to cover it, at least in one or two problems. And they say whichever one is most convenient. The second one I doubt we'll use, but it's available. It has a lot more to do with like the application, right? So if you're an engineer, you might use one as opposed to the other one depending on what the application is. Dietitians would probably use this one a lot. If you're doing work with space, you measure pressures and stuff. The ATM is atmospheric pressure and stuff like that. So anyways, let's move on to the next thing. Those are the values. So a hot air, or the air inside this hot air balloon that's flying over Malaysia is hotter than the ambient air. As a result, the balloon experiences a buoyancy force, which forces it up. And really what's going on is because the air molecules on the inside of the balloon are bouncing around a lot, they're pushing upward, but also they're pushing outward. But the buoyancy force just means that you want to move from a higher pressure to a lower pressure to a higher pressure, and so that just forces the thing to go up. So think of like water, right? The less dense material will float higher than the more dense material. Air is air, but because the hot air is more kinetic and moving more, there's less of it needed to fill the balloon. So there's less air, less density, right? There's less air molecules inside of this, so it'll want to rise above, okay? And so the air pressure, it's kind of interesting, the air pressure will kind of push the higher air pressure on the bottom. It's almost like a wing on a plane, okay? That's what causes, a wing on a plane works on the same principle, right? So if this is a wing, since we're going to start talking about fluids, when this wing does this, there's not as much air here, so this is a low pressure, okay? And then this is a higher pressure. And I think I misspoke earlier. But so what happens is the air molecules down here will push up. We kind of have the same thing here. The air molecules here, which are more dense than this, will push up. And as you go higher into the atmosphere, there's less pressure because you're further away, gravity, all that comes into play. Well, what does that mean? Well, it means atoms and molecules typically are widely separated. That's why they're a gas. Because the forces between them are weak, these distances and properties of gas depend more on the number of atoms per unit. And temperature can have an impact on their kinetic energy. So if I hit this with a bunch of heat, and we think of volume, right? So volume is stuff that's contained, right, in a set volume, right? So we'll think of this as a container. And if I heat that up a lot, what'll happen is this molecule might bounce outside of that container, or I'm not able to fit more molecules in because these are bouncing around so much. And so pressure and volume and temperature are all related. Pressure is really something in a container that pushes out. So the pressure when that molecule hits that and pushes back, that's pressure. Okay? Now if this container can expand, that will be the volume, right? Because we can expand the volume of a balloon with more pressure inside. Does that make sense? And then the temperature has an impact on all of it. And so you can actually, if you condense the volume of something, you can actually create pressure and increase the temperature, and vice versa. So these, I remember I was talking to the VP from or actually the president of Contigo mugs. They make coffee mugs, and their coffee mugs keep coffee hot for a really long time because it's pressurized. So because the pressure's there and the pressure doesn't change and the volume doesn't change, the temperature has to be the same for a longer period of time. It comes out a little bit, but you could pour a cup of coffee in one of those Contigo mugs and leave it in. But also when you open it, you gotta be careful because sometimes it'll shoot out and get you. Okay. All right. So when air is pumped into a deflated tire, the volume first increases without much pressure. In other words, we're not expanding. The air molecules are going in, and as they go in, they kind of push out, and they fill the tire up. But that's not a lot of pressure. In other words, if you look at the pressure here and compare it to the pressure when the tire is completely flat, not a whole lot. But as you get more and more air molecules in there, in the air tire, it's going to push out harder and harder, and that creates more pressure. So now we've got a little bit more pressure. And then at some point, when you get pretty close to the tire being full, you will actually get an increase in temperature. So if you take a tire, that's also why when you have a tire, if you buy the tires in the summertime, this happens to me all the time, I always buy tires for my car in the summertime, and they put the tires on my car and it's pumped up. In the winter, that first cold day, the sensors go off in my car and say you need to put air in your tires, because what happens is the temperature has cooled off the air on the inside, and it doesn't have the same level of kinetic energy, so that the pressure decreases because it's not bouncing off the tire as much, and the volume of the tire decreases too. And so the sensor goes off and says you got to put like a couple pounds of air in there and you're good. So they're all related through that ideal gas law. So let's try to do some of these problems, okay? So I'm going to do a couple of examples with you before I make you do some of the stuff. So we have, let me find this problem on the thing here. So we have a bike tire that's fully inflated with an absolute pressure of 7 times 10 to the 5th pascals, right? And that's just under 90 pounds per square inch at a temperature of 18 Cs. What is the pressure after the temperature has risen to 35 degrees? Okay. So we've got to list some things. So if I reread that right, the initial pressure, because remember pascals is a measurement of pressure. The original pressure is equal to 7 times 10 to the 5 pascals. And then your original temperature is equal to 18 degrees Celsius. And then your final temperature is 35 degrees. Okay. Well, it says assume there is no change in volume. So then our initial volume is equal to our final volume. Okay? And there are no leaks. So that means the initial number of particles is equal to the final number of particles. Yeah. Yeah. So, one of the things that we could do, and I don't know if you guys want me to derive this or not, but I can take we know that the relationship between the final pressure and volume will be equal to the final capital N K, and we'll do a little bit of fixing on that, over F, right? And also, I'm going to have the value where there's a relationship between the initial pressure and the initial volume, and that is equal to NO KTO. So now the interesting thing about this is we said that the volume is basically the same, right? So they're constant. So now if the volume is constant, and also if our number of particles are the same, then I wrote down Avogadro's. I meant to make this a capital N, so just make this a capital N, right? Because there's no air leaks. So they're the same, so this reduces down to 1, right? And this reduces down to 1. And then the constant, Boltzmann's constant, reduces down to 1, right? So do you understand what I'm saying when I say K over K equals 1, right? And then I'm skipping the step where you would just substitute in one of these for the other, and so you'd have NF over NF or NO over NO. And so then what we end up with is, and I'm going to write it over here, we have PF, the final pressure, over the initial pressure should be equal to the final temperature over the initial temperature. And again, we had to do a little bit of work, but we have 3 of the 4, and we're trying to find the final pressure. So if I multiply both sides, because that's what it asks us to do, is find what is the pressure after the temperature has risen. So I'm going to multiply both sides by the initial pressure, right? So then I get the final pressure is equal to the final temperature times the initial pressure divided by the initial temperature. And so I'm just going to plug that in. The final temperature was 35. And then the other thing that we got to do is we've got to think about, I've got to convert these temperatures to Kelvin. So remember, and it's interesting, we do but we don't, because they're both gonna, yeah, we do. So remember, we have to convert these to Kelvin, and then this one has to add up to 273, right? Or you add 273 to it. And so my final temperature would end up being, not, instead of 35, it would actually be 290, or no, 308, right? Am I doing the math right on that? 308 times the initial pressure, and I think we've got to, I think we can leave it in pascals. So then we can leave pascals as pascals. So that's this times 7 times 10 to the 5th all over the final temperature, which I think is 291, yeah?
Yeah.
Okay.
Maybe yours from-
Yeah.
I filled out the thing.
Yeah, you filled out the thing. Go ahead. And I'm gonna. Do you guys have this written down so I can clear this out?
Yeah.
Yeah. Okay. So, so then, the final pressure then, if we did all that math, is just going to be 7.41 times 10 to the 5th pascals. Or yeah. Is that what you guys got?
Yeah.
Okay. So very similar to the other physics stuff, right? We have a bunch of stuff. We got to find an equation. We got to plug some stuff in. Some things will cancel out, and it's always fascinates me. You'll have 3 of the 4 things you need, and you're solving for the 4th. Got a question? Yeah.
So it's always convert to Kelvin, even though the Celsius.
Yeah.
cancel
You
out?
guys probably don't remember that. We just covered that with physics. So with the Physics 1 kids. For the SI unit, it's always going to be kelvins. Now, in some cases, you can leave it as Celsius. Like, so the assignments that you did the other day, you could leave it as Celsius because, I'll give you an example. If you say 25 degrees Celsius minus 10 degrees Celsius, well, that's just going to be a difference of, 15 degrees Celsius, right? So that's all Celsius stuff. But now, if you convert that, what's 207? Wait, when do you guys get the door for me real quick? What's 273 plus 25? Is that 298?
Yeah.
298 degrees Kelvin minus, and then, thanks. What's 10 degrees? Well, that'd be 283, right?
Yeah.
283 degrees Kelvin. Well, that's still 15 degrees Kelvin. That's the difference. So whenever you do like delta T, and that's part of the formula, you're okay. But outside of that, and I think that you guys had a problem too where you had to figure out where Fahrenheit was the same temperature as Kelvin.
I think our first assignment.
Yeah. Yeah.
Ultra version.
And that's just a coincidence, that's all. It's just a one-time deal. But yeah, so for physics, everything should go to Kelvin. But sometimes in your homework, you could leave it as Celsius and it doesn't matter. But you technically should convert it to Kelvin. Okay? All right. Let's keep going with the notes. That was just example 1 from our notes. All right, so the next one is how many molecules are in a typical object, such as the air tire. We can use ideal gas law to give us an idea of how large N typically is. So we want to calculate the number of molecules in a cubic meter of air at a standard temperature, or STP, which is defined at 0 degrees Celsius at atmospheric pressure. Okay, so same thing. This whole section is about ideal gas law. I wonder if I could change my pen settings. No. So, PV is equal to capital N times Boltz's constant, right? And that's how many molecules you have, right?
Please excuse this interruption. There are 3 cars currently parked in the bus lanes and the...
So just to kind of recap, yeah, that was correct. That is the right answer. So we just basically do ideal gas law, they gave us all this stuff. We had to remember to change this to Kelvin, and then when you plug all the stuff in, I was a little bit off on my approximation on the orders of magnitude, but that's okay. Yeah, and then you just plug it in, and that's the number of molecules. Okay. Do you guys have any questions on that one? Yes. Everything. Well, I'm recording a video. You can look at that later. Okay. Let me see. Let's see what the next slide is. There was basically this one. We're just going to do a bunch of problems, and then we go from there. This is Avogadro's number. You guys should know this. This is how many particles. Yes.
Can I use my phone to take a picture of this and copy it?
Just this once. So this is the number of particles in 1 mole, right? And yeah, that's it. That's all I got. So write that down. You guys know, I think we wrote that down in the beginning, didn't we?
I think so.
No, I said we'll come back and write the numbers in later. So yeah, make sure you write this down.
What's like the mole -1?
It's just a unit. So when we plug it in, so you got to remember when these scientists come up with these numbers, these are a constant number that they found every time. And so they're like, well, this number's the same all the time. But when you calculate this constant, there's units attached to it, right? And so that's how many molecules. It's like saying 6.02 times 10 to the 23rd parts or particles per what? Per 1 mole. So remember, if I have A over B, that's the same as, and remember this is B to the first power, that's the same as A times B to the -1. Okay? And we have to include that in there because that's what we're measuring. We're saying that it's 6.02 times 10 to the 23rd particles, but it's per 1 mole. And so we can't just throw the mole out. And so it looks a little weird because it's raised to the -1. Did that help? Okay, good. All right, can I move on to the next one? Okay. How big is a mole? Well, on a macroscopic, on a larger scale, macroscopic, I want to say scale, but it says level. 1 mole of tennis balls would cover the Earth to a depth of about 40 kilometers. So that's a lot. Remember, it's 6 followed by 23 zeros. Okay. So that's an interesting tidbit. So you don't need to write anything down there. Let's do one more calculation, and then I'm going to give you guys your homework. Yeah, dude. It says calculate the standard number of moles in 1 cubic meter of gas at STP. And then part B is find the number of liters of gas per mole at STP. Okay, so, oops. Remember that the number of moles, so it says the number of moles in 1 cubic meter. Or you could replace this with per. And so if you replace that with per, you would have N moles over meters cubed, right? And so then you have capital N molecules, which is different than moles, per meters cubed. I'm gonna have to write this on a different platform than Google Slides. I just don't like the way the marker looks. And that is molecules per meters cubed. On the next line, I gotta plug in the numbers, right? So one of the things at STP, we said, we just did the math on that, didn't we? That's 2.68 times 10 to the 25, right? So we're gonna plug that in here for N. That's literally N at STP. Does that make sense? We just calculated that. So what I'm going to do is I'm going to say 2.68 times 10 to the 23rd. And then that's going to be molecules per meters cubed. All over Avogadro's number, which still stays the same. And that's going to be molecules per mole. Oh, I'm sorry. This is per mole. That wasn't meters cubed. That's molecules per mole on the denominator of the fraction. Okay. And so 10 to the 23 and 10 to the 23 cancel out. And so then if you do the math on this, you're going to get about 44.5. And so the molecules will cancel out. And then you're left with your units. It's going to be, and it's the inverse, right? Because
I thought it was 10 to the 25 for,
you're right, it's 10 to the 25. I said cancel out, but yeah, you're right, it's 10 to the 25. That's why we have 44.5. Otherwise, it would be 0.445. And because this, and do you understand why we flip-flop these? Because they're both in the, yeah. So this becomes, this goes down to the bottom, and then the moles come up to the top. So that would be moles per meters cubed. Yes.
Can I use the restroom?
Yes, you can. I think that's it on the notes for today. Do you guys have any questions on that stuff? You probably have a lot.